Okay, so this is Lecture 2, Part 4, which corresponds roughly to Section 2.4 of your textbook. And so today's lecture will discuss the definition of the limit of a function and how we can use this definition to actually write mathematical proofs of why limits exist. So I'm going to start off with an example. Let me paste one into the Smart Book. Let's see, pull up a graph here. So this graph, I believe, is out of your textbook, but I'll paste it in here for reference. Okay, so here I show a graph, and let me go ahead and write down what the definition of the function is. It's a piecewise defined function, and here it is. So I have f of x is equal to, piecewise defined now, so it's a multi-part, it's equal to 2x minus 1 if x is not 3. And it's equal to 6 if x equals 3. All right, so you'll see this hole right here, this indicator hole at x equals 3, and then you'll see this discontinuity, and then the function is actually assigned the value of 6. All right, so the question is this. Oh, that's too big, is it? Let me see if I can make it smaller. I guess not. Okay, I'll go ahead and write it then. Okay, so let me rewrite the question here. How close to 3 does x have to be so that f of x differs from 5 by less than 0.1. All right, so it's kind of a tricky question, and a lot is being asked for in this question. But basically, what we're after is, okay, so we have a hole at 3, 5 on this function, okay? And the question is, we want to make arrangements for an interval on the x-axis. In other words, I want an interval on the x-axis that contains 3. See, I've accentuated an interval on the x-axis, and 3 is in this interval. All right, and so what I want is I want to design an interval or construct an interval on the x-axis such that the output of any number that I select on this interval accentuated in red, okay, ranges from 5.1 to 4.9. Okay, so here we go again. If I pick a number, any number x, except for 3, I'm not going to pick 3, but I choose any number on this red interval that I've accentuated in x. Okay, I desire, and then I take that number that I pick, any number on the red interval except for 3, and then I plug it in to my function. I plug it in here to my function. Okay, I want the output of my function to be between 4.9 and 5.1. All right. So that's what I mean by this statement. I choose a number on the red interval, plug it in, except for 3, plug it into f of x, and then my output is not a number now, but it's it's contained. My output is contained within between 4.9 and 5.1. All right. So effectively, what I'm asking for is, can we kind of, in a sense, describe the left and right endpoints of the interval? Okay, so that's what we're chasing. That's what we're pursuing. All right, and I'm going to give you the procedure for finding, essentially, the endpoints of this interval. Right? Okay, so the endpoints, yeah, so here we go. So the procedure goes as follows. Step number 1, okay, we let the absolute value of x minus 3 denote a distance. Okay, so this is actually a distance from 3. And of course now x is the number in our interval. So let me write this carefully. Okay, so let me switch colors. X. So when I write a red X, I mean an X selection on this red interval. Okay? So X minus 3. Okay? What does this mean? Okay, so we go back to geometry, and this is the distance from 3. Remember, a geometric distance is a positive number. We don't have negative physical distances. All right? So visualize this, okay? Choose a number x, okay, and x minus 3 is the distance x is from 3. So for instance, if x were 10, then 10 is 7 units from 3. If x were minus 10, then minus 10 is 13 units from 3, okay? All right, so that's obvious. Now by the same token, okay, f of x f of x minus 5. Okay, so the absolute value of f of x minus 5, well, that is the distance f of x. Well, actually, that's the distance from f of x to 5. Distance from f of x to 5. Okay, so we have this result. All right, so we understand the two distances. It's pretty fundamental. Now we want to take these two pieces of information and we want to organize it in some sort of mathematical relationship. So the third step of the procedure is this. We want to find delta, and this delta is shown in the graphical illustration right here. We want to find delta. Now delta is just a variable, okay? Find a delta, Greek letter delta, such that the distance f of x, the distance from f of x to 5, okay, this distance is less than 0.1. Okay, remember, we want to be within, we want the distance f of x to 5 to be less than or equal to 0.1. Okay, this distance is met if what? The distance from 3, okay, is less than delta. All right, and x cannot be 3. All right, so this is the hardest part of the task. All right, so if I choose an x such that the distance my x is from 3 is less than delta, some delta which I have not specified yet, okay, because delta is a quantity we need to find, okay? Delta is a quantity we need to find. And if I find this delta, if I'm successful in finding this delta, then a correct choice of delta will result in my being less than 0.1 units from 5 as for the output, okay? So if I choose a delta such that my input is, say, the distance, my input, my distance from 3, okay, the distance, okay, so perhaps I should phrase it this way. My distance from 3 is less than delta, okay? I visualize a delta such that my distance from 3 is less than some delta, then my function's output, okay, for that choice of delta, my function's output for that choice of delta will always be 0.1 units from 5, okay, if I choose my delta correctly. And delta is kind of like, again, it's kind of an upper limit. You see, it's greater than. It's an upper limit for a range of x's. Okay, so in other words, I have a choice. I have a prescribed set of x values I can choose, namely those x values on this red line interval. And if I choose my delta correctly enough, okay, I have the largest possible set of values of x, so that when I take any value of x from that set and I plug it into my function f of x, then my f of x will never stray more than 0.1 units from 5, okay? And so my delta is the cap. It's kind of a cap, an upper bound, a limit value, which tells me how many or what values of x I have a choice of selecting, okay? So 3 minus delta would describe my left endpoint, and 3 plus delta would describe my right endpoint. And all the numbers between those two endpoints would be values of x I can choose to plug into f of x, so that f of x never strays more than 0.1 units from 5. Okay, that's the task that we have to figure out. So the name of the game is to find this value of delta, which defines these endpoints, which defines kind of a subdomain. The red axis you can consider to be a subdomain, such that whenever I pick a value out of this subdomain, the subrange is on the interval between 4.9 and 5.1. So we can kind of consider this as a subdomain and this is a subrange. And the values of the subdomain are mapped into the values of the subrange by this peculiar function f of x. All right, I know that's a mouthful, but try to hold it together. So here's how we compute delta. All right, so we need to find a value for delta, preferably a numeric value. All right, so translate it mathematically, what we have is this. We have the absolute value, or distance, because absolute value is a distance function, minus 5. That distance is less than 0.1 if the distance from 3 on the x-axis is less than delta. Now, I've put this piece right here. Right here, 0 is a lower bound, okay, because if I write this, then this means that x can't be 3, okay? If I plugged in 3, I would have 0, but this is a strict inequality. So putting this here means that I have to exclude 3 as a value for x, all right? So what is my delta? How do I calculate my delta? All right, so here's how. What we do is we go ahead and plug in the definition for f of x. Not the point, yeah, since x is not 3, okay, so x can't be 3, so what is the definition of f of x? All right, so when x is not 3, f of x is defined as 2x minus 1, okay? So plug in the definition. All right, simple enough. Okay, since x is not 3 because of this piece right there, okay? Now, all right, so let's go ahead and manipulate what's inside of the absolute value here. So simplifying the algebra, we have 2x minus 6, right? And we can factor out 2. So we have 2 times the absolute value of x minus 3. You can factor absolute values. Okay? And we require this distance to be less than 0.1. Okay? We require that distance to be less than 0.1. So what happens if I divide both sides of this inequality by 2? Well, it turns out if I do that, which is equal to 0.1 divided by 2, which is equal to 0.05. All right, so now compare this expression symbolically, okay, and mathematically, of course, but just match this expression that I have in the box with our objective. We require that x minus 3 be less than delta, and remember, we want a number for delta, or some expression for delta. Well, if we compare this statement, we see that we have a value for delta. It pops out. It popped out, right, by manipulating the previous math statements. So our choice for delta is 0.05. Okay. All right. So we have a conclusion here. We can conclude if x is within a distance of 0.05 from 3 on either side of 3, then f of x will be within a distance 0.1 from 5. Okay, so that's how it works. Okay, all right. So now we can take this idea, this very specific example, and we can generalize it into the definition of a limit. All right, so here's how. Let me go on to another page. Generalize. Oops. Okay, replace 0.1 with a, with insert. Oh, I tell you what. Why don't I use the math calculator? Let me rewrite this. Let me rewrite this using a more appropriate text style. This won't work. All right, so generalize. Replace. Oh, that's not going to work either. Okay, well, I guess I'll just handwrite it. All right, so let me handwrite it because I need to use Greek letters. All right, so we want to replace 0.1 with the Greek letter epsilon. Okay, because and epsilon said, suppose we don't want 0.1, suppose we want 0.5, or suppose we want 0.0001. Okay, and replace 0.05, which was our delta, with delta. Okay. All right. So in other words, instead of using hardwired numbers in the previous example, we're going to replace them with variables epsilon and delta. Okay. And then once we do that, a definition emerges. A mathematical definition emerges. Okay. Let f be defined on some open interval that contains the number a except a itself. Okay, and we saw that in the previous example. Okay, what happens then is we get this result. The limit as x approaches a of f of x is equal to L. Okay, we have this limit. If okay, now I'm going to write some mathematical symbols and I'll explain what that means. Okay, I may already have. So upside down A, like this, means for all. Okay, so rather than writing out the specific words for all, I'm going to write down an upside down A. Okay, so this limit equals to L if for all epsilon greater than 0, okay, there exists. Okay, so the backwards E is another math symbol, which means there exists. It's kind of hard to read that. Let me write it again. Okay, so backwards E means there exists. All right, so the limit as x approaches a of f of x is equal to L if, for all epsilon greater than 0, there exists a delta greater than 0. Okay. All right. Now, the backwards epsilon means such that. Okay. Such that if the distance from A, so if the distance from A is less than delta, then the distance from output L is less than epsilon. Okay, so if we can show this, if we can take any positive number, okay, what it means is if we can take any positive number on the y-axis, any positive number on the y-axis, and call it epsilon, and with that positive y number, we can find a corresponding x on the positive x-axis, okay? We can find a corresponding x value that we call delta on the positive x-axis. If we can do that for all, so for all positive y's, okay, we can find, so for all positive y's, choose what positive y. And with that positive y, if you can find a positive x value such that the distance that x value is from A, okay, then the distance from L, okay, will be less than epsilon. If we can do that, then the limit exists. Okay? So the trick is for any positive y, I need to find a delta value. I need to find a delta value. If I can't find that delta value, then this limit does not exist. Okay? So if I can find a delta such that, okay, I'm within say delta units of A. I'm within delta units of A. And if I'm within delta units of A, and if I'm correspondingly within, say, epsilon units of L, okay, if that happens for all choices of epsilon, then the limit exists. Okay, so that's what that means. If I can find it, again, I can't emphasize this enough. If for any positive y, okay, I can find for any selection of a positive y value, I can find a corresponding selection of a delta value, which is a positive x value. Okay, and I choose an x that's within delta units of A, and if that selection of x that I chose that's within delta units of A produces an output that is within epsilon units of L, okay, the limit exists. All right, and the strategy is we need to find the delta. So again, let me emphasize this again. I'm sorry to belabor this. All right, so I choose a positive y value, okay? Then I find a corresponding positive x value that matches my positive y value, okay? I do that. And all right, so basically I choose a positive y value, all right? And so that positive y value means that, well, let me kind of sketch it. Here's my y-axis. All right, here's my L. This is L. L is a number. All right, now I choose some distance from L that's bounded above by epsilon and bounded below L minus epsilon. All right, so I choose this. Okay, so here's my requirement. Then suppose I come along and say, okay, I'm going to choose, say, this y value right here. And of course my function, who knows what my function is going to be. All right, here's my function, okay? And all right, so I choose this, say, hypothetical choice for epsilon, and then I pick a y value on this interval, epsilon, L minus epsilon to L plus epsilon. So I choose my y value, and then, okay, so I say, okay, what value of x for the given function produces this particular output? All right, so here's an x. All right, now, can I find a delta? Can I find a delta such that if I choose delta appropriately, actually this is an x, this should be a. So let me make this a. I should write it better. Let me go to extend the page and zoom in on this diagram. All right, let me do it better. Sorry. Here's what's going on graphically. All right, so yeah, that might be a better way to present the argument. All right, so here's my y-axis. Here's my x-axis. All right, and then I draw, and then I have some hypothetical function shaped like this. Okay. Now what I do is, here is my L value. Now the objective is, I want to know if x approaches a, if f of x is equal to L. All right. So, well, anyhow, here is L. All right. And so what I do is I choose epsilon. Okay. Epsilon is any positive number on the y-axis. All right. And so my choice of epsilon does this for me. It defines a range of y values. Okay, so this is, and I do this for any epsilon that's greater than 0. Okay, here's a specific case of an epsilon. Now, if I need to find a delta, if I can find a delta based on this particular arrangement, then the limit will exist. So in other words, okay, all right, so we would hope that we would hope that at A, okay, f of A would, okay, so what I'm basically trying to ascertain is this. We don't know if f of A is equal to L. F of A may not be equal to L, but what we really want is this. Okay, so let me draw my function up like this. Okay, what we really want is we want this. This would be my delta right here. Okay, this would be my delta right here. Actually, we have kind of an asymmetric situation. So we know that f of delta 2 produces an output of L plus epsilon. F of delta 1 produces an output of L minus epsilon. All right. So I need to find a delta. So if I say if I come along and make this my choice for delta, the smaller of the two deltas. All right, so I call this delta, and I call this delta. All right, so if I choose any value on this symmetric interval right here, if I choose any value of x on this symmetric interval where a is in this interval, okay, and I evaluate the function at any choice of x on this particular interval, my output had better be somewhere between these two numbers. Okay? So if I choose any number on this interval that contains a, all right, and I calculate my output for this blue function, I better have if I can find an output on this green interval, then the limit as x approaches a of f of x is guaranteed to be L. And this has to be the case for any positive epsilon. So I can choose epsilon anywhere on my positive y-axis. So the strategy is calculate this delta. If I can find a numeric value for this delta, then this limit, this is a true statement. If I cannot find a delta, such delta, that is not a true statement. Okay, so that's what that means. All right, so it has to work for all positive epsilons. Okay, all right. So it's a challenge to explain this technique at times. So it's best done with examples. Yeah, there's a nice illustration in the book, and let me go ahead and show that to you. Okay. Yeah, so next page. So here's an illustration that kind of reiterates what I just spent some time talking about. All right. So again, the red curve is my function, and so here's what I want to know is the fundamental concept. That is this a true statement? Is this true? Okay, so I start off by saying, okay, well, here's my L value. So here's the graph y equals L, right, this dotted line. Okay, and then I start, okay, so I choose some hypothetical epsilon, which is a positive y value, okay? And then I form the so-called strip, okay? This is a strip. You see what constitutes the strip? The upper boundary of the strip is L plus epsilon. The lower boundary for the strip is L minus epsilon, okay? And then I identify my A. Here's my A value. And what I want to know is if I were to draw this vertical line A right here, okay? All right. Okay. Does this vertical, okay, so the question is, will this vertical line x equals A intersect with the graph, or not necessarily intersect, but will it, well, not necessarily, okay, if I can find, oh yeah, okay, so here's, put it another way. Okay, you see what, let's go back to this strip. Okay, find where this strip, the upper boundary of this strip right here, let me shade it in green. Okay, so first of all, from a geometric perspective, identify the upper bound of the strip and look at the point where the upper bound of the strip intersects the function. Okay, now take this intersecting point, okay, and drop a perpendicular to the x-axis. Okay, and then next, identify where the lower boundary of the strip, right here, which I'll accentuate in blue. See the lower boundary of the strip? Okay. Now, drop a perpendicular from this intersecting point where the lower boundary of the strip and the function intersect. Okay, where at that point of intersection, drop it to the x-axis like that. Okay, so now if I can find my A value on the ensuing interval defined by these 2 points, the green point and the blue point. Okay, if I can find my A in there, then I've established the existence of a delta. Okay, now it may be the case that we have an asymmetric interval. In other words, A is not in the center of the interval. Okay, so for instance, let's call this point delta 1, and we'll call this point delta 2. Okay, so it may be the case that delta 1, A minus delta 1 does not equal to A minus delta 2. These two distances may be different. So in this case, if that is the case, then the choice for delta would be the smaller of the two, without exception, at least insofar as this class goes. All right, so minimum means you take the smaller of the two numbers. Okay, so if A is found in such a interval on the x-axis, then this is a true statement. The limit exists. Okay, and note that we usually form this rectangle right here. You see this rectangle that's kind of shaded in a reddish pinkish color? If you can find such a rectangle, then you can find a delta. And once you find the delta, then the limit exists. And of course, this will be true for any choice of positive epsilon. This illustration right here appears to be the same. Does it not? Yeah, it's the same. I'm not sure why I have it twice. Okay, so the idea is to find, identify this particular strip, identify these points right here, and then if your A is on the interval, then you can establish a delta, and then the limit is validated. Okay, so that's what we're going to be doing, validating. All right, so the strategy then is just simply to find the choice of delta. You can actually even use a graphing calculator to show you something. So let me give this a go. Okay, yeah, so we have a number of examples to work tonight. So next page, I'll pull up the math calculator. So let me insert the web page in the browser. So okay, so let's consider this function. Y is equal to x cubed minus 5x plus 6. Okay, and that is shown in red on this graph. All right, so the problem I want is, or the question I'm asking is, so there's the graph right there. We want this. The limit as x approaches 1 of x cubed minus 5x plus 6. Okay, so this is what we're chasing. All right, and so let me add another caveat to this question. Okay, I want to find a delta. I want to find a delta. I'll go ahead and write it out. Find a delta such that, if I'm delta units away from x equals 1, then I'll be 0.2 units from the output of 2. All right, since this is a polynomial, okay, we know that polynomials, we know that polynomials exist for all values of x. However, in this particular case, we know that f of 1 is 2. Okay, so if you plug in 1, you'll get 2. 7 minus 5, yeah, okay, just checking. All right. So, but I'm asking for a little bit more. I'm trying to push it a little bit harder on this. And so here is 1. So let me go ahead and plot x equals 1. Okay, and let me go ahead and graph y equals 2. Next curve, y. Will not let me type. Oh, it's typing in there. Ah, come on. Technology. Try it again. Y is equal to x cubed minus 5x plus 6. All right. So now it's shown in purple. And then x equals 1, shown in orange. And then y is equal to 2. Okay. Shown in black. Okay. So does it not show y equals 2? Y is equal to 2. Please show. It doesn't show y equals 2. All right. It's too bad. Okay. Oh, yes, it does. It does show. Okay, so let me zoom in. Okay, so here, of course, is the point. All right, so the purple graph is x cubed. So what we want to do is we want to find a delta so that we are no more than 0.2 units from 2 in either side. So 2, 4, 6, how are these grid cells arranged? 1, 2, 3, 4. So this is 0.25. So what I want, so how about if we graph y is equal to 2.2. All right, so that'll be shown in blue. Okay, so the blue line is y equals 2.2, and y equals 1.8. Okay, and that's shown in green. All right, so here's our strip. The strip is defined by the blue and the green. Okay, and all right, so now we want to find our deltas, right? We want to find a value of delta so that this point right there, that point right there, okay, we want 1 to be bracketed by an interval. Okay, so can we find a choice for delta? And by the way, this will be a web assign. You can use this technique to answer a number of web assign questions. So will that go away? Why are these things not moving? Okay. Yesterday I couldn't get them to stay. Now I can't get them to go away. Let me zoom out. Okay, double click on them. Makes them go. Okay, so yeah, so here's our strip. right here. Okay, well, that's not a very good coloring, is it? Okay, so our strip is above the blue line, below the green line. Now, let's draw a vertical line where the blue line intersects the graph. Okay, so let's make it purple. So how about we do this? Okay, so we draw this line. Okay, and we could draw another line, say, I guess I could do it in green, where the graph intersects for the first time this green line. Not here, but here. Okay, well, you could draw it here. No, draw it here. Draw it so that you're as close as possible to the vertical line x equals 1. Okay, the first intersecting point to the vertical line x equals 1. This is the first point. This is the intersecting point that's closest to the vertical line. Okay, choose intersecting points that are closer to the vertical line if the graph intersects the strip in more than one point. All right, so our choices then. All right, so in this case, what is the abscissa? What's going on here? Okay. I guess I got to zoom in some. Okay, so zoom back. Okay. So what is it's annoying now. They change the programming on this graphing calculator all the time. It's a little bit dicey to handle. Go away, please. All right. Okay. This isn't working very well, is it? Instead of, okay, I want this point right here. Okay. So note that the coordinate of this point is 0.9114. So our delta 1 would be, this would be our choice for delta 1. Well, let's see here. Actually, our choice for delta 1 would be, this is our x value. This would be our choice of our x value. So we could say that delta 1 is equal to 1 minus 0.9114. Okay. It's a distance now, so it has to be a positive number. Now, if I pan to where the, okay, so where the graph intersects the bottom portion of the strip for the first, and it's closer to x equals 1. So the coordinates of this point would be, at least the abscissa of the intersecting would be 1.124. So my choice for delta 2 then would be delta 2 is equal to 1.124 minus 1. Okay, so now I take the smaller of these two numbers. Okay, I'm not sure if they're the same, so I'm grabbing my calculator and I'm checking that. Okay, so 1 minus 0.9114, 1 minus 0.9114 is equal to 0.886. And then 1.124 minus 1 is equal to 0.124. Okay, so 0.8, so delta 1 is the smaller number. So delta 1, delta, which is equal to delta 1, is equal to 0. Let me check it again. 1 minus 0.9114, 0.0886, 0.886. Okay. So what this means is, okay, so the way I dealt with it was I developed this strip defined by where the function intersects 2 plus epsilon and where the function intersects 2 minus epsilon. And then my a value was x equals 1, so I drew a vertical line, and then I figured out the two intersecting points on the upper boundary of the strip and the lower boundary of the strip that were closest to the vertical line x equals 1. Okay. And then I used that as a foundation for calculating my delta. Okay, so I found those 2 points right here. So you see how I found the coordinates of those 2 points? And then I calculated the distance from 1, okay, from 1 to these points, okay, along the x-axis. All right, so the distance from 1 to the ordinates, no, I'm sorry, the distance from 1 to the abscissa of these two intersecting points. So understand where I got the two intersecting points from. Then I calculate the distance from 1 to the abscissas of these two intersecting points, and I have two choices for delta. Then I chose the smaller delta. So that means, what that means is, if I desire to be within 0.2 units of 2 for this function, then I have to be within 0.886 units of 1 on either side. If I go outside of 0.886, then I lose my guarantee that I will be within 0.2 units of 2. All right? So you see how that works? Now, WebAssign will have a couple of questions like this, and so use this Desmos calculator to calculate those particular, or to find that particular value of delta. Okay, and I'm looking to see what the solution is. Yeah, the solution in the book was 0.08. Okay. All right, so this isn't really a proof. It's just it's a specific example. We need to find a delta that works for all positive epsilon. All right, so to generalize this problem, to note that the limit exists, the limit as x approaches 1 of f of x is equal to 2, we need to do this for every positive epsilon, okay? Which, and of course, we did it for epsilon equals to 0.2, but of course, how many positive epsilons are out there? Well, an infinite number. So we really have to do it for every positive number. And obviously, we can't do this an infinite number of times. So we need a more formal way of, or a more compact way of demonstrating that this limit exists, okay? But this would be a graphical example of one case. So let's do a formal proof. All right, so next slide. Let me draw the function. Let me grab a picture of the function. Okay, so in this case, the problem is we want to prove that the limit as x approaches 3 for 4x minus 5 is equal to 7. We want to prove this, okay, without using direct substitution. Okay, and so the blue line shown in this illustration is 4x minus 5. All right, And here I've identified, you see in red right here, a subinterval, a subdomain on the x-axis that contains 3. And you see that 3 is, the left endpoint of the red subinterval is 3 minus delta, the right endpoint is 3 plus delta. And here there's a red subrange on the y-axis where 7 is contained in the subrange, and 7 minus epsilon is the lower bound, 7 plus epsilon is the upper bound. And of course we want to find delta for any epsilon greater than 0. Okay, for any epsilon greater than 0. So if we can find a delta, if we presume that such a delta exists, then this is what would happen. If such a delta exists, oops, if x is a delta distance from 3, okay, if delta exists, and if x is a delta distance from 3, then our output f of x minus 7, our output for the given choice of x will be an epsilon distance from 7. Okay. All right. So can we find such a delta? If we can, then this statement will be true. Okay. So again, we'll plug in the value for f of x. So if for a delta distance if we're no more than a delta distance from 3, then we're no more than an epsilon distance from f of x. And I'll plug in the value for f of x, which is 4x minus 5 minus 7. Okay, and since we're taking absolute value, epsilon has to be greater than or equal to 0. But in this case, since I'm using strict inequality, epsilon cannot be 0. All right, so now I manipulate the right-hand side. I manipulate the then portion of the statement, so I'll simplify. 4x minus 5 minus 7 is the same as 4x minus 12. It's less than epsilon. Then I'll factor out a 4. So 4 times the absolute value of x minus 3 is less than epsilon, which implies that absolute value of x minus 3, or the distance from 3, must be less than epsilon over 4. Okay. All right, so what this means is if I choose a positive value for epsilon and I plug it in to this equation right here, I'll have a positive value for delta. So thus, I have an expression for delta. Epsilon is the independent variable, okay? Epsilon is any positive number of your choosing. So no matter what epsilon you choose, I can find a delta such that if I'm within delta units of 3, then I will be within epsilon units of 7. That's what that means. Okay, if I'm within delta units of 3, I will be within epsilon units of 7. And that holds true for any positive epsilon. So no matter what positive epsilon you throw me, I'm going to be able to find a delta. And because of that, this is a true statement. That's all you need to do. There's truth in that statement. Okay. So here's how we can verify the correctness of the proof. Okay. Here is the check. Here's how you check. So I think there may be a WebAssign problem or two that asks you to check this result. And the way you check is just like I said, given epsilon greater than 0, choose delta equal to epsilon over 4. Okay? So, now go back to your if-then statement. If we're within delta units of 3, then what? F of x, which is 4x minus 5, minus 7, is equal to 4x, absolute value of 4x minus 12, which is equal to 4 times the absolute value of x minus 3, okay, which we know to be less than 4. Now the absolute value of x minus 3 is less than epsilon over 4. Well, we know that absolute value of x minus 3 is less than delta. And then we know that delta is equal to, our choice for delta was epsilon over 4. And so that's equal to epsilon. So we've recovered our if-then statement, our original if-then statement. So if this, then this, which is equal to epsilon. Okay. So your choice for delta, if you plug it in to your original if-then statement, and you get back epsilon as the final step right here, then your proof is correct. Okay. So by definition of limit, okay, by definition of limit, the limit as x approaches 3, 4x minus 5 is equal to 7. Okay, so with polynomials, these epsilon delta proofs are pretty easy. All right. Let me see what's in, okay. So these proofs also work for left and right hand limits. So let me give you an example or some definitions in an example. A couple of definitions. So the definitions, the formal definitions for left and right-hand limits. All right, so our definition for the left-hand limit, okay? X approaches a from the left of f of x. This limit is equal to L if, for any choice of epsilon positive, there exists a delta greater than 0, and the colon means such that if x is between a minus delta and a, okay, then the distance from L, the function's distance from the output of the function, its distance from L, will be less than epsilon. Okay, and I believe I may have an example. Okay, and then the right-hand limit, conversely, the the limit as x approaches a from the right of f of x is equal to L if, again, for any positive epsilon, there's a delta that's positive such that if x is between a and a plus delta, then the output of the function for the choice of x will be an epsilon distance from L. So that's what that means. Okay, so these two definitions, you can see the if statement, the inequality in the if part is the only variation in the definition. So for instance, where this becomes useful is suppose we want to prove, or we use those definitions will be in something like this. For functions like, if we want to prove limits of a natural log of a function or a square root of a function, we want to know if that limits exist. So let me show you one. So prove that the limit as x approaches 0 from the right of the square root function, square root of x, is equal to 0. Okay, obviously we can't approach 0 from the left because the square root of the function is not defined for negative values of x. Okay, so we use the right-hand limit. Okay, since this is a right limit, so we'll use the definition of the right-hand limit. All right, so it goes. In this case, this is our a. Our a is equal to 0. So I'll refer you back to the definition on the previous slide. So if, all I'm going to do is just wire in the values for f of x and a into that definition. So if x is between 0 and delta, okay, then the square root of x minus L, okay, so here's our L. This is our L value. So I'll go ahead and wire that in. Must be less than epsilon. Okay, and now, so the absolute value of a square root function is, you can just take away the absolute value here, right? Because the absolute value of square root is still the square root because the square root is always a positive number. So this means that the square root of x must be less than epsilon. Okay, so if x is a delta distance from 0, then x is an epsilon squared distance. Then x is less than epsilon squared. Okay, so we're an epsilon squared distance from the output. Okay, we're an epsilon squared distance from the output. So basically what I did was I squared both sides. All right, so it's almost trivial now. So our choice for delta then would be epsilon squared. So choose delta equals to epsilon squared. All right, so now we have to verify that this choice for delta will work. Now obviously epsilon squared is always going to be a positive number, so that means that delta will always be a positive number. So that's one check. So another check is, so let's do the check. Okay, so given epsilon greater than 0, let delta equal to epsilon squared. Okay. If x is within a delta distance of 0, then the square root of x is less than the square root of delta, and we said that delta is equal to epsilon squared. Okay, and the square root of epsilon squared, of course, is just epsilon. Okay, and so this implies that now we can dress up the square root function into a format that's consistent with f of x. The absolute value of f of x minus L is less than epsilon. Okay, so by definition, of right-hand limit, RHL, the limit as x approaches 0 plus of the square root of x is equal to 0. Okay, so we have that. All right. So our first taste of formal proofs involving limits. Okay, now let's add a little bit of complexity to the problem. Sometimes it's not always so clear as to how to calculate delta for more complex functions. So next example. I want to do is prove that the limit as x approaches 3 of x squared is equal to 9. All right. Now, we can't do this graphically because we have to, the proof has to encapsulate the facts that it has to work for all positive values of y, or epsilon. Okay? We can't just pick one point on the function and show it for one function. We have to demonstrate it for all values of epsilon. So, and here's the proof. All right, so it starts out as follows. If this limit were to exist, okay, then this statement must hold. If we're a delta distance from 3, okay, if we're within delta units of 3, which is what this statement means, then the output of f of x must be within epsilon units of 9. All right, so if this is true, then we should be able to find a delta for any positive epsilon. All right, so in doing so, we have this result. If so what I'm going to do is I'm going to factor this difference of squares, and I'll have this. Okay, now the strategy so far has been to make the then portion shaped like the if portion. And so usually up to now, up to this point, this factor right here was usually a number, okay? And we would take this number and we would swing it over to the right-hand side of the inequality, basically epsilon divided by a number, and call that delta, and we're done. But we can't do it in this case, okay? We're stuck. The dilemma is right here, x plus 3, okay? So what we need to do, so the strategy is, okay, the strategy is we need to find a number a number we'll call C, find C, I'll call it uppercase C, such that x, the absolute value of x plus 3 is less than C. Okay? Less than C, not epsilon. Make that a C. Because if we can do that, then we can use our customary technique of swinging it over to the right-hand side. We'll have an epsilon over cap C, and that will be our choice for delta. Okay? So we need to find basically an upper bound for the factor x plus 3. And that looks kind of strange. How can you find an upper bound for x plus 3? Okay. All right, so we have to be kind of arbitrary here. And so to find C, okay, so if we found such a C, well, let me show you again. If we found such a C, we would have this. We would have this. It would look like this. And then we would extend that so that x minus 3 absolute value would be less than epsilon over C, and life would be nice, because then that would be your candidate for delta. Okay, so to find C, all right, so we have to do kind of a subproof now. Here's the procedure. Restrict x to lie in some interval centered at 3. Okay, do that. Okay, so how do we make this restriction? What's a convenient way to decide what this interval is? So we need to decide on what this interval is. What is the easiest possible way to decide an interval? Well, the easiest way out. Okay, so obviously we have a gazillion choices. We have a gazillion choices for intervals where 3 is centered, right? So what is the easiest possible interval that we can design so that 3 is centered in some arbitrary interval? Okay. So how about we do this? How about we make an assumption? Now we're designing such interval, okay? So in designing such interval, we'll assume x is within a distance 1. A distance 1 from 3. Okay? And so if we do that, if we make that assumption, then we'll have this. So if x is within a distance 1 of 3, we have this. And look, if we just make this assumption, we have a choice for delta. So, yeah. So there's your choice for delta. Delta's 1. make delta 1. But the problem is, okay, so there's a potential problem for this. Will this choice for delta, in other words, will all the choices for epsilon work for this particular delta? Okay. Well, it could be the case that for all the choices of epsilon, they may produce a choice of delta that's, say, greater than 1. And if that's the case, we're good, because we always choose the smaller of the 2 deltas, as we've shown in the previous examples. However, it may be the case that for some choices of epsilon, okay, and I'm talking about the graph, visualizing the graph. Some choices of epsilon may depend, some choices of epsilon may produce a choice of delta that's less than 1, okay, in which case 1 cannot be the correct choice for delta, okay? So, repeat, some choices of epsilon for this limit problem may produce a delta which is less than 1. We have to explore that potential, in which case we would have to use that delta and not 1. Okay, so let's continue on. Okay, so that's why we need to find a value of C. Okay, so the way we make the determination of the fact that there could be some deltas for given epsilons that are less than 1 is if we think that they exist, or we have to rule out the fact that they exist or not, we have to compute C. We have to find the value of C, okay? And the C will indicate if there are deltas which are potentially less than 1 for this particular problem, okay? So let's continue on, and here's how we calculate C. Well, we have this inequality, so we'll use the content from Lecture 1, and we know that, so we need to convert this inequality, how do we, well, let's continue on. So we have, by the definition of absolute value being less than the number, this result. Okay, so we know this from algebra. Okay. Now, if I were to add 3 to all the sides of the inequality, now remember, I'm trying to calculate C, so I'm going to add 3 to everybody, and so I'll have 2 is less than x, which is less than 4. Now, what did we say C was? Okay, C is the upper bound for x, absolute value of x plus 3. So I have to take this absolute value being less than the number, I solve for x, and now, of course, as you would expect, I'm going to add 3 to all the sides of the inequality, and then I convert the inequality into an absolute value. Okay, well, clearly, the absolute value of x plus 3, okay, to get C, C is the upper bound of the absolute value of x plus 3. And if I were to take the absolute value of x plus 3, then the absolute value of x plus 3 must be less than 7. Okay, and there is your C value. That's your C value. Okay, so now we have 2 restrictions on the absolute value of x minus 3. Okay, so extend the page. So now we have two restrictions on the absolute value of x minus 3. Okay? The first one is 1. Okay? The first restriction was our arbitrary assignment, the arbitrary case. The second one was when we calculated C. Okay? When we calculated C. And so that meant that the absolute value of x minus 3, so when we plug in C, go all the way back, and we plug in C here, here's our C, which was equal to 7, then we discovered that absolute value of x minus 3 is less than epsilon over C, which is epsilon over 7, because 7 is the upper bound for the absolute value of x plus 3 for this problem. Okay, so So to make sure that these two inequalities, so to make sure that these two inequalities are satisfied, we have to take the minimum of our choices for delta. So to make sure that the two inequalities, the if-then statement is satisfied, take delta equal to the minimum of those two choices, which would be 1 and epsilon over 7. So now we have found a choice for delta for any choice of epsilon. So if epsilon, say, were 10, then delta would be 1. If epsilon, say, were 1, then delta would be 1/7. And you can verify that graphically. Go back and draw a graph. All right, so of course we need to check, is this true? All right, so is this true? So go back and do our check procedure. Given epsilon equal to the minimum of 1 and epsilon over 7. So if invoke the if-then statement. So if we're a delta distance from 3, then so we plug in our first choice of delta, then x minus 3, the distance from 3, less than delta equals 1. So a 1 distance from 3 is the same as saying x is between 2 and 4. And this is the same as saying that the absolute value of, or the distance from 3, the distance from positive 3, the distance from negative 3 is less than 7. All right, so we have this inequality. Also, now plug in your second choice for delta. And what does this mean? This means, now, so we take this expression right here, and we take this expression right here, and we multiply them together. So we have x minus 3 times the absolute value of x plus 3 is less than epsilon over 7 times 7, which equals to epsilon. So therefore, the triangle formed with dots means therefore the limit as x approaches 3 of x squared is equal to 9. All right, so there's the conclusion. Okay. All right, so we can use this epsilon delta concept. Let's see if I can paste it. All right, so let's prove one of the limit laws. The limit of a sum of functions is equal to the sum of their limits, right here. Okay, and this is, let me touch this up a little. This is L, and this is M. All right, so how do we prove this? Well, use the old technique, epsilon delta. So prove that the limit as x approaches a of f of x plus g of x is equal to L plus M if we have these two limits, okay, shown right here. So here's how. Okay, so we let epsilon be greater than 0, and we want to find a delta such that if okay, we're within an epsilon distance of the sum of the functions. We're within epsilon distance of L plus M. Okay, so we want to, can we find such a delta such that this if-then statement is true? Okay, so we have this notion of triangle inequality. So by triangle inequality, we have the distance f of x plus g of x minus L plus M. This distance is equal to, I'm going to split the sum, or use an associative property technique here, f of x minus L plus g of x minus M. All right, so let's do an associative technique at the outset right here, okay? And we know that to be less than or equal to, okay, so we can split this absolute value into a sum of two absolute values and substitute in the inequality portion. This is triangle inequality. The triangle inequality stipulates that the sum of the lengths of two sides of a triangle is always greater than the length of the remaining side, the third side, okay? And that's what we're just portraying here. Okay, it works for functions as well as in addition to triangles. All right, so we have this. Okay, so that's what triangle inequality offers us. Okay, so now the next thing we want to do is we want to make the distance from L in terms of epsilon. We want to make that less than epsilon over 2, and I'll use E for epsilon. I don't want to have to go and hunt for Greek letters using this editor. And we'll make the distance from M less than epsilon over 2. Okay? All right. So since epsilon over 2, okay, is greater than 0, okay, right? Since that's greater than 0, and we have this. Okay, so let me plug in the math thing. Okay, so since epsilon is positive and we have this, we're given this piece of information. Okay, so pick up the editor. There exists a delta 1 such that, okay, if 0, okay, by definition, if we're a delta 1 distance from A, then we're an epsilon over 2 distance from L. Okay, that's one thing. And there exists a delta 2 such that if we're a delta 2 distance from A, okay, then we're within an m distance of the output for that given. We're within epsilon over 2 distance of m for g of x, that is. Okay, so we have that result. Okay, so now we have two deltas, so let delta equal to the min of delta 1 and delta 2. Okay. All right, so now we need to solve for delta in terms of epsilon. Okay, so if we're within a distance of delta now from A, okay, then we're obviously within a distance delta 1 of A. And we're in obviously a distance delta 2 from A. Okay. So as a result, the distance between the output and L for F is less than epsilon over 2, and the distance of the output of G from M for the given value of X is less than epsilon over 2. So we combine these two facts. So therefore, if we sum the two, we have f of x plus g of x minus L plus M. By triangle inequality, that's less than or equal to f of x minus L plus g of x minus M, okay, which is less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. Okay. All right, so that was the verification. Okay, so we can find if the limits of the two functions exist, then the limits of the sum of the two functions exist as well, because we can find a delta for any given epsilon of the sum of the functions. Okay, all right. So that's a proof of one of the limit laws, and you can do the same thing with the subtraction as well. Should be able to do the same thing with the subtraction. The proof will involve a few minor differences. All right. So now let's talk a little bit about infinite limits. Okay, epsilon delta proofs with infinite limits. Okay, so next page. So we'll talk about the limit as x approaches a of a function equaling to infinity. So if we have an infinite limit. So a couple of definitions. Okay, the first definition is right here. Let f be defined on some open interval, okay, right here, shown, that contains a except possibly at a itself. So we say the limit as x approaches f of x is equal to infinity, as shown in this drawing, if for all m, so for any choice of m, there exists a delta such that for this given delta, okay, if we're within a delta distance of a, as shown on the x-axis, then the output of the function will be greater than m. So if I choose any x on this interval, this subrange right here, my output for any choice of x, except at a, of course, is guaranteed to be greater than m. And if that guarantee holds, then this will be our limits right there. Okay, so that would be the limit as x approaches a of f of x. That's a definition. Now, how about the limit as x approaches a of f of x equals negative infinity, conversely? All right, so again, we define our interval right there, and if for any choice of x on the interval, except a, of course, if we choose that x and the output, okay, the output is less than this negative number n, okay, for any choice of x, if it's less than n, then this limit holds. Okay, so the trick is finding a delta and an n. Well, find a delta so that this works for any n less than 0. Okay, so we have to find a delta so that this relationship holds for any negative n, and if that's the case, then this limit holds. All right, so I'll do an example using the first definition. So we want to prove this result. The limit as x approaches 0 of 1 over x squared is equal to infinity. All right, so we'll use the first definition from the previous note. So the way we deal with this is choose an arbitrary m greater than 0. Okay, now we need to find a delta. So find a delta such that if where delta units from x, remember our a value is 0, then our output for a choice of x is greater than m. Okay, all right, so can we find such a delta? So here's how we can. 1 over x squared greater than m. Since both quantities are positive, I can take the reciprocals of both sides, and so I have x squared is less than 1 over m. Okay, and then I can take the square roots of both sides, and so remember the square root of something squared is the absolute value, is less than 1 over the square root of m. Okay, and so there's my choice for delta. So let delta equal to 1 over the square root of m. Okay, so we can, for any m greater than 0, we can find a delta, which is just 1 over the square root of m, like that. Okay, so that's the proof. All right, using proof that the limit as x approaches 0 of 1 over x squared is equal to infinity. All right, so now I want to finish off this section with a couple of examples that might help you do the project on Chapter 2. You have enough material now to get started on your Chapter 2 project. There may be 1 or 2 more technical points, but you can get started on some of the questions. So I'll just work a couple of representative examples. Let me search for some that I created. Let's see here. Let's do another proof of a quadratic. So let's pull my notes here. See, I want to do quadratic, and I want to do this one. Okay. Okay, so a couple of examples. Or we have to calculate a C value. The book didn't have too many representative problems, but so I'll be a little more rigorous here. So let's do this. Let's prove the limit as x approaches 1 of x squared plus 3. So I don't know. How about what's more interesting? Is that one interesting? No, it's not very interesting. Let me do another one. That one's too easy. I want to do a harder one. Let me erase this. How about the limit as x approaches 2 of 3x squared minus x is equal to 10. Okay, so how do we prove that? All right, so here's the proof. Let epsilon be greater than 0. Okay. Find a delta. Which depends on epsilon. Okay. So that if we're within a delta distance of 2, remember this 2 is your A value, then we're within an epsilon distance of 10. For the given output. Okay, so just as before. All right, so what do? We begin with f of x minus 10 is less than epsilon, and solve, and I put that in quotes, solve for the absolute value of x minus 2. Like that, like so. Okay, so all right, so then what happens is, if we were to do this, then okay, absolute value f of x minus 10 is less than epsilon if, and only if, okay, I plug in the value for my f of x, which is 3x squared minus x, minus 10 is less than epsilon. Okay, and this is true if and only if, okay, now I'll go ahead and factor this quadratic, okay, so in factoring it we have if and only if 3x plus 5 times x minus 2 is less than epsilon. Okay, and this is true if and only if, so we can factor the absolute value of a product into the product of the absolute values. The absolute value of 3x plus 5 times the absolute value of x minus 2 is less than epsilon. Okay, so what do we do? Replace replace 3x plus 5, the absolute value of 3x plus 5, okay, with c, a constant c, with c, and keep x, absolute value of x minus 2. Okay, since we wish to solve for the absolute value of x minus 2. Okay, so assume to replace 3x plus 5 absolute value, assume delta less than or equal to 1. Okay, so if that's the case, if delta is less than 1, so we have this. We have the absolute value of x plus 2 is less than delta. Okay, and so this implies that uncoupling the absolute value of x minus 2 is wedged between -1 and 1. Okay, and so simplifying, solving for x, we have what? 1 less than x less than 3. Okay, and if I multiply both sides, all sides of the inequality by 3, I'll have 3 less than 3x less than what? 9. Okay, and then I'll add 5, so I'll have 8 less than 3x plus 5 less than 14. Okay. Okay, so it follows then that 3x, it follows that the absolute value of 3x plus 15, I'm sorry, 3x plus 5, it follows that the absolute value of 3x plus 5, okay, is less than 14. All right, so with this notion, right, we'll substitute in to the original inequality for f of x. So f of x we said was less than epsilon. All right. So we once had this expression being less than epsilon. But we now have an upper bound for the absolute value of 3x plus 5. Okay. And as promised, that has to be less than epsilon. And this is true if and only if, okay, 14 times the absolute value of x minus 2 is less than epsilon. And this is true if and only if the absolute value of x minus 2 is less than epsilon over 14. Okay. So now choose delta is equal to the min of 1 and epsilon 14. As we did in the previous example. Okay. So there you have it. There's your choice for delta. So that's the proof. Okay. All right. Let's do a harder example. Okay. All right. So next page, last example for this particular section. So I want to prove the limit as x approaches 3 of 2 divided by x plus 3 is equal to 1/3. All right, so how do we deal with this? Okay, so again, let epsilon be greater than 0. Find delta. So that if we're a delta distance, if we're a delta distance from 3, then the distance from the output and our limiting value is less than epsilon. Okay, so we want to transition, we want to solve for x absolute value, we want to solve for this quantity x minus 3. Okay, so we want to solve for that. Okay, so solve for this using this. Okay, all right, so let's do that. So absolute value of f of x minus 1/3 is less than epsilon if and only if, plug in your value for f of x, 2 divided by x plus 3 minus 1/3 is less than epsilon. Okay, if and only if. Okay, so now I'll do the subtraction, and when I do the subtraction, I'll have 6 minus x plus 3 divided by 3 times x plus 3 is less than epsilon. Okay, and I'll simplify that. That would be if and only if the absolute value of 3 minus x over the absolute value, oops, I'm sorry. Sorry, I got my absolute values crossed. Try it again. I'll distribute the absolute values. The absolute value of a quotient is the quotient of the absolute values of the factors. Okay, so we have this. Okay, so ultimately we get here. Okay, now I'm going to do a trick. And this trick is not in the book, so something that will prove useful. So this is true if and only if. What I'm going to do is I'm going to factor out a -1 from the numerator. Oops, I still have those split, don't I? Okay, and 3 times the absolute value of x plus 3 is less than epsilon. Okay, and so the absolute value of 1 gets tossed. Okay, so because I can take this product of absolute values and express it as, I can do this. I'm kind of cheating when I do this, but I can split those into 2 absolute values. Okay, so and then this term goes away like that. Okay, right? Kind of tricky, isn't it? Okay, so if and only if the absolute value. Okay, so we have this result. All right. And so what it all boils down to is we have if and only if 1/3 times the absolute value of x minus 3 times 1 over the absolute value of x plus 3 is less than epsilon. Okay, so what do we do next? Okay, go to another page. So replace the absolute value of x plus 3 with a constant, with C, with a constant C, and keep the absolute value of x minus 3, since A was 3. Okay? All right, so assume, as always, delta is less than or equal to 1. Okay? Okay, so if that's the case, then, okay, we have absolute value of x minus 3 is less than 1. This comes from our if statement. And we'll have negative 1 is less than x minus 3, which is less than 1. And we want to transform this into an expression of x plus 3. So if I add 3 to everybody, I'll have 2 less than x less than 4. And then if I add 3 to everybody, I'll have 5 less than x plus 3 less than 7. What happened? Where am I? Less than 7, okay? And so if I take the reciprocals of everybody, I'll have 1/5 less than 1 over x plus 3, which is greater than 1/7. Okay? And so what does that mean? That means that 1/5 is our choice for C. All right, so C is equal to 1/5. That's our upper bound for 1 over x plus 3. Okay, so now using, so going back to the prior statement involving epsilon, we had this. We had 1/3 times x minus 3, absolute value of x minus 3, times 1 over the absolute value x plus 3. We had that as being less than epsilon. Okay, but we also know this now. 1/3 times the absolute value of x minus 3, and we know the cap for 1 over x plus 3 is now 1/5, and all of that is less than epsilon. Okay, so now we have, this is true if and only if okay, well, yeah, I don't need that. I don't need this. Okay, so we have this result. Okay, so where do we go from here? So, I'm sorry. Okay, so this is true if and only if. All right, we multiply the constants. 1/15 times the absolute value of x minus 3 is less than epsilon. Okay, and this is true if and only if the absolute value of x minus 3 is less than 15 epsilon. Okay, so now choose delta to be the minimum of 1 and 15 epsilon. And that pretty much completes the proof. Okay, so thus, if, therefore, okay, so therefore, if we're a distance 3, we're a delta distance, we're a distance delta away from 3, then we're a 1/3 distance from the corresponding output for the choice of x. And because we found a delta, okay? Because of this fact that we found a delta. Okay, so that's all I want to do with epsilon delta at this stage of the game. I have a number of examples, some harder, some easier than this. So if you want to send me an email, I can give you some more problems if you want to work in this area. I would encourage you to work more advanced problems in this topic, especially if you're planning on majoring in mathematics or engineering, because these kinds of problems will present themselves again in a similar style structure. So this concludes the lecture I have for section 2.4 of the book. Yeah, so you can start your project now. You can do a fair amount of Chapter 2 web assigned problems, and email me if you have any questions. Okay.